the incandescent light bulb invented over 100 years ago gives off a nice glow, coming very close to natural sunlight. However, it loses almost 90% of the energy as heat, and only 10% of the electricity is converted to light. Over the last 50 years, the lighting industry has moved towards more energy-efficient technologies, like the compact fluorescent and LED light bulbs. Both of these are 4 to 5 times more efficient as compared to the incandescent light bulb, and require photoluminescent materials to produce light that is as pleasing to the human eye as sunlight. The photoluminescent materials absorb the light from the LED and convert it to a light of longer wavelength. For example, most LED lamps use blue LEDs, and blue light from the LED is converted to yellow light by the photoluminescent material. The blue light from the LED and yellow light from the material combine to form white light. Semiconductor nanocrystals form a special class of photoluminescent materials, and their properties are greatly dependent upon their size. The nanocrystals, as the name indicates, have dimensions smaller than 100 nanometer in size. At this scale, these materials exhibit properties different from individual atoms or molecules, as well as bulk materials which are several micrometers or millimeters in size. To understand how these nanocrystals work, let's go back to the atomic scale. The electrons in an atom are arranged in discrete energy levels. As the atoms come closer to form bonds, the energy difference between the excited and ground states decreases, and eventually, the discrete energy levels are replaced by bands of continuous energy levels separated by an energy gap. With increase in the particle size and number of atoms in the crystal, more energy levels are continuously added, and the energy gap between the bands gets lowered. Therefore, the energy gap of a nanocrystal is lowered with increasing particle size, and this variation in energy gap with size causes the variation in the wavelength of light emitted by the nanocrystal. Lower energy means longer wavelength, and thus, the wavelength of light emitted by these materials increases with the increasing particle size. These materials are desirable for use in lighting due to tunability of their properties with size as well as higher efficiency as compared to other classes of materials. Since these materials are even smaller than the wavelength of light, they do not exhibit any reflection or scattering of light, like bulk materials, and behave more like transparent films over LEDs. This almost doubles the light output from the LED bulbs made with nanocrystals. So, how are these nanocrystals synthesized? And since most of their properties are size-dependent, strict control of their size during synthesis is of utmost importance. To understand the synthesis procedure, let's take the example of cadmium selenide nanocrystals. To make cadmium selenide nanocrystals of various sizes, separate solutions containing cadmium and selenium ions are taken. In these solutions, cadmium and selenium ions are surrounded by polar groups in the solvent that keep the individual ions far apart from each other. As these two solutions containing cadmium and selenium ions are mixed together at high temperature, the ions react to form cadmium selenide. Cadmium selenide molecules keep forming in solution, and the particle growth continues as long as the reaction temperature is maintained. Thus, nanocrystals are continuously removed from this solution and cooled down to room temperature to lock them at particular sizes. The crystals isolated sooner are smaller in size than the ones isolated after some time has passed, as the reaction continues. To summarize, photoluminescent nanocrystals exhibit superior properties as compared to photoluminescent bulk materials, and thus are preferable for use with LED-based light bulbs. Due to their size, they do not scatter light, and thus act as transparent films, letting maximum amount of light to pass through them. Also, they have higher efficiency of light-to-light conversion, leading to greater energy savings and lower cost per unit light output.